All right, welcome everyone. Good morning. I'm James Ward. I work on developer experience at AWS for QDeveloper and some other stuff. So this talk is on structured concurrency. I also have Ryan.
Ryan Knight, CEO at Grand Cloud, boutique consulting company. I also have a couple other roles I play. I'm currently a cloud architect at Audio Enhancement, helping them transition from a on-prem to a cloud solution, and also a technical advisor at Berry Fertility. So,
awesome. Okay, well, let's dive in this morning. Try to wake you up with some lovely diagrams. So let's start with what is structured concurrency. So we have to look back at just concurrency in general, where it's kind of just like the Wild West. You can do a bunch of stuff. It gets really hard to deal with semaphores and mutexes and all the different ways of doing concurrency. And structured concurrency tries to simplify the model for how we do concurrency. So the structure of structured concurrency generally is a hierarchy. It's kind of like a tree. So what we do is we have our kind of main task that's happening, and then we create a scope. And the scope is this way to delineate a boundary and create the actual structure. We then put children tasks into the scope, and then there's different ways that we can decide what happens to complete the scope or say that we're done. But one of the ways that is, we won't show today an example of this, but there is an example I'll talk about a little bit, is to say once all of the children have completed, then take all of the results, put them all into a package, and then return out of that. And so this is kind of the basic model of structured concurrency, is this like fan out and then wait for all the results and fan back in and then complete the thing that had been spun off.
And I think you can compare it to traditional concurrency, which is unstructured, because you're unstructured and you fan out all your tasks, but there's no structure to that fanning out, and there's no way to cleanly join those back together because they're all unstructured. So.
Yeah, and in that model, you have to maybe come up with some way to create the structure using mutexes, using whatever, and it gets really nearly impossible and messy to deal with.
Your callback health and trying to chain your callback health together and join them together in this completely unstructured way, so it's really messy.
Yeah. So that's kind of our basic introduction to structured concurrency. There's a lot of elements that typically come into structured concurrency, like how do we deal with errors, how do we deal with cancellation, how do we deal with resource management, and we're going to go into some examples of those as we go. So one of the most common places that we use structured concurrency is to do a race. And this is not a race condition like the bad thing that you don't want. This is a race like, imagine like a running race or a horse race or something like that. And so with a race, what we have is structured concurrency, but for a specific use case, which is I want to spin off one or more child processes, tasks, and then as soon as I get a successful result out of one of those, so as soon as one person crosses the finish line, take all the other racers and, I don't want to say kill them, that sounds terrible, but take all the other ones and cancel them. And because
you just tell him to stop. You're not killing them.
That's it.
You just ask him, like, quit doing your work. You've done
That's
enough.
Right. The race is over. You've lost. I'm sorry, but no need to continue running.
Don't waste the energy on your horse. Like, save it for later.
Exactly. That's a good positive spin on it. So with the race, what we're doing is we're doing that fan out, but then on the fan in part, it's as soon as one task completes successfully, that's when we're going to consider the structured concurrency scope to be completed and return the result back. So that's our race. Cancellation is an important piece of that because a lot of times in a race, we don't want it would be wasteful once we've gotten our result, it'd be wasteful to let the other processes continue running. And so there's some different ways that you can deal with cancellation. When you're in the world of virtual threads with Loom or a number of other concurrency systems, there is good ways to do cancellation. So if you're waiting for a web service to get back to you, you're waiting on that response, you can cancel that while you're waiting, and then that'll just close the connection out, and then if you're in like a hot loop where you're iterating through a bunch of stuff, it can be a little bit harder to deal with cancellation, but there are ways to do that. But ultimately, you do want to be able to provide cancellation to those tasks that are the losers of the race. Okay, so that's our basics of arrays. We'll see some code for that in just a few minutes. So as I was diving a couple years ago into trying to understand structured concurrency, I was like, I think there's some like common use cases for structured concurrency, common things that come up with error handling, with cancellation, with some higher level constructs like timeouts, like hedges, and we'll get into some of those. So I came up with this thing called Easy Racer, and Easy Racer is a set, it's like an obstacle course for structured concurrency. What it does is it provides a server with 10 different endpoints and then a bunch of different clients. And the clients, what they do is they go through the obstacle course and try to see if they can get the right answer to the problem at hand. So 10 different ways to do concurrency. And then I started by creating a bunch of implementations of this. And so I've created some Scala ones, some Kotlin ones, a Java one, and then some other people have come along and created some other ones. So I got some help with the Rust Tokyo one. Somebody built the Go one for me. There's been some great contributions to the OCaml ones. Python ones have been kind of challenging. I did a JavaScript one, which really tested my abilities with writing concurrent code. So lots of different implementations to show how do different languages and frameworks do structured concurrency given these obstacle courses? And so you can go check out many different implementations. We're going to focus mostly today on the Java Loom one, and we'll also show a Kotlin one and some Scala ones as well, just to contrast some of these things on the JVM. But yeah, go check out the different implementations. It's really kind of fascinating to see how different languages and frameworks deal with structured concurrency. You've done some Go structured concurrency, and how do you feel about
I wouldn't
that?
call Go structured concurrency. Go has unstructured concurrency. There's a really good blog post out there that kind of puts it into light, which talks about why Go routines are considered harmful, and it compares it to a traditional go-to, like the old school BASIC where you had the go-to and you couldn't, you're trying to trace the path through your program. Well, Go routines ends up something very similar where you have no idea like where things are happening and what the structure is, and then trying to do a race condition gets really complex.
Yeah.
It makes it really challenging. Yeah.
Yeah, so the Go one doesn't really shine in this one. I will say the best implementation that I've seen for Easy Racer is OCaml's EIO co-HTTP. It's really nice structured concurrency in OCaml. So yeah, it's a fun one to look up.
Yeah, when you started this, I thought, oh, Go will be easy to solve these, and then I realized, oh, Go doesn't really have a way of racing, and it makes it a huge mess to try to solve the race problem. So
yeah. So check out the Go one if you're interested in some fodder for why Go's structured concurrency is not super awesome. Okay, so let's talk about some high-level approaches to structured concurrency, and then we'll get into some code. So there's different ways that you can do structured concurrency. We're going to be focused mostly today on what is like the scope-oriented way of doing structured concurrency, where you create a scope and then you create children in that scope, child tasks in that children's scope. And in the world of Java Loom, there's a JP 453 that added a structured concurrency scope that makes it gives you a nice API for doing this scope-oriented structured concurrency. You don't have to use that with virtual threads, with Loom's virtual threads, but it definitely makes a lot of sense to do so. And so we'll see some code for that in a little bit. This scope-oriented way of doing things, Ryan mentioned the blog post on Go. It's called "Go to Considered Harmful Structured Concurrency." It's like it's like the blog post that kind of invented structured concurrency. The person that wrote that created a Python library for structured concurrency, and they call this scope-driven a nursery. And so you create children in the nursery. Or something. But it gets a little weird talking about how you cancel those children.
Yeah.
So
the analogies are pretty bad there, but it makes it easier to understand. Like that nursery is taking care of all the children inside that nursery, and then it's just giving some of the children back to its parents when they're not needed anymore. So
terrible, Ryan. Okay. The next style is direct style, and so there's a few different things you can go to Easy Racer. We'll show a little bit of the Scala aux one just to show like, all right, if you have Loom and you have virtual threads and you have JP 453, what kind of APIs and DSLs could you put on top of that to make the interaction with the structured concurrency maybe a little bit cleaner, a little more concise? And so we'll look at that one. Rust also has a direct style that's based on futures, which we're not going to show today. And then there's effect-oriented. I just finished writing a book on effect-oriented programming with Scala Zio, and I'll show a little bit of this today. Don't want to spend too much time on it, but the effect-oriented stuff, I really like this approach. There's two different kind of styles of effect-oriented. There's the monadic approach that Scala Zio does, and then there's something called algebraic effects, and algebraic effects are what languages like Unison, Rock, OCaml are doing for their way to do effect-oriented programming and structured concurrency. So some interesting stuff there. We won't go into that today, but you can go explore these all in the Easy Racer repo and see how they compare in actual code across the obstacle courses. Okay, so let's get into some code. So in Easy Racer, there's scenario 1. Scenario 1 is an easy one. We're just going to do a basic race. So the basic race is we're going to have a connection. We're going to open it to a server, to my Easy Racer server. Then we're going to open a second connection to the server. We have to open both at the same time. That's the concurrency part, is being able to open two connections at the same time to the server. And then the first one that returns a response is going to be the thing that we're looking for. It's going to be just a string that says right. You got the right answer. And then the other one, the server tries to do some things to make sure that make sure that you're doing things in the right way. And so it actually will take that second connection that is open to the server, the loser, and it'll actually just keep that connection open forever. The server will. And so you won't actually be able to complete the race, in this case, if you don't cancel and close the loser of the race. And so there's some things that the server does to try to make sure that you are doing structured concurrency in the expected way. And so let's dive into some code for this one. So this is the Scala aux version of this, and so pretty concise. We're just going to make a def, so this is our way to be able to repeat this request. It's a def, not a val, because a val would just get the result out. So we create a def for our request. We're going to send it to the back end. We're going to get the body of the response. And then in aux, there is a high-level construct called a race, and we give it two requests. We're going to make two requests. And that's all we need to do. We get a string back. Because this is based on Loom underneath the covers, there is no, it all look async. It's not, underneath the covers, it is async. It is non-blocking on the I/O channels here. But from our perspective, it's this direct style. It looks imperative. It doesn't look like it's actually non-blocking thanks to Loom underneath the covers. And so we're going to race our two requests, and sure enough, this all works.
I think the nice thing is that it returns a string. It doesn't return an async of a string or a future of a string. It's just a string.
Just a string. Just a string. So it looks imperative. No constructs there for the async bits. So just to show you what this actually looks like, we've got our Docker server running with the Easy Racer server, and then I can come over and just run this one, and we'll see, hey, we opened a request to /1 on the server. We opened a second request to /1 on the server, and then we received a response you can look up the IDs here, but the second one was the one that we got the response on, and the body was right. And so in this case, I got the right answer. We can also go check the server and verify. The server in this case outputs the number of concurrent connections. So we'll see where we are at 1, then we go to 2, then 1, then 0. So sure enough, it got cleaned up, that connection that the server was just leaving open forever. When it was canceled on the client side, that closed the connection, reclaimed the resources there for the connection, and allowed our race to complete, and we get the right answer. So that's kind of the simplest one for the race here, and it's doing all the right things. It's passing all the tests here for Scala aux. So let's look at the same thing for Java Loom, and this is just using standard library stuff with the new JP there. And so what we do in this case, we've got our way to build a request here. So we're just using standard JDK stuff. But then here's the structured concurrency part of this, is we're going to use a try with resources. We're going to create a structured task scope, and we're going to say, all right, shut down this scope, so complete this scope when we get a successful racer. So as soon as one of our racers completes successfully, now shut down the scope and return the result. So then we're going to do our scope.fork. This is how we add tasks into the scope. So scope.fork, we're going to make our request out to the server. We're going to do that twice, so we have 2 racers. And then I'm going to do a join. So when I do this join, that's essentially the part where I'm now like blocking forward progress. And because it's based on Loom, not actually blocking, but that's where I kind of sit there and wait until I get a response back from the server, and then then it proceeds and it does do the cancellation of the other loser as well, and then I return the result. So I pull the thing that was the winner out with that dot result and return the body. So that's the Java Loom version, and it all works as expected, and the contract with the server, with the closing and cancellation, all that stuff works as expected. So pretty straightforward on that one. Anything to clarify? Okay, so let's look at Kotlin coroutines just to contrast that. So Kotlin coroutines is a way to do structured concurrency, but Kotlin coroutines doesn't have a good like race in it, and so it takes a bit of work to do a race. Kind of unfortunate. Hopefully the standard library will at some point get a better race, but Easy Racer is about showing, a lot of the scenarios are about showing races, how to do races, and so you can do it in Kotlin coroutines, but you do have to do some manual management of doing the forks, essentially, and then doing the cancellation there. So yeah, I like Kotlin a lot, but this races are maybe not one of the areas where the standard library shines. There are some other libraries that you can use in Kotlin, like Arrow or one called Splittease, that do have some higher level race APIs on top of coroutines. But just out of the box, coroutines, not a little clunky there for creating a race. Okay, so then Scala Zio, I want to show this one. This is what my book on effect-oriented programming was about, was using Scala Zio. These are effects. And so very similar to the aux one, but we're using this like direct style on top of a monadic operation. And so this is kind of, it looks nice and clean with this defer, nice YAML-y syntax there, but this is still non-blocking. The one thing that I like on this one is that I can take a effect, and this can happen on any effect, in my case an HTTP request, and then there's a race combinator function on that, and then I can pass the second one. There's also the API where I can say race and give it a list of effects to race, but it's nice to be able to just take an effect and then say .race with another effect, and that creates gives me the winner. And then, of course, all the other things with the cancellation and stuff managed for me in there. Okay.
And I would say if you want to learn about effects, I'd highly recommend James' book. It's the best explanation of effects I've seen. So
I appreciate that. So. Okay, so let's go on to scenario 2. Ryan, tell us about what happens with errors.
So what we want to do on this one is send 2 requests into the server. The server is going to wait for those 2 requests to be made into the server, and then it's going to cancel one of those requests. In a traditional, like if I were to do traditional like async HTTP requests, that's actually a hard scenario to handle because one of those requests is going to time out throw an exception. And so I want to be able to cleanly figure out which of those 2 requests are throwing an error and then return the result of the other one. So the way to visualize this is, right, I create my scope. I have 3 children in this scope. Each of them are, forked off in parallel. One is going to complete successfully. One is going to throw an error. Maybe one's going to cancel out. But what I don't want to happen is when child 2 throws the error, I don't want it to blow up the parent scope and propagate that scope up. What I want it to do is to have that scope kind of contain that error and wait to see if one of the other children completes successfully.
So that one, what we're showing on this one is there is another way to do this with, is you can say, as soon as there is an error from a child, propagate the error out, like essentially race, but as soon as an error happens, then continue. And that's not the scenario we're going to be
right,
doing today.
Okay, right. There's the race shutdown on success and the race shutdown on error. So there's kind of 2 different ways of handling those scenarios.
Yep.
Right, and so with Java Loom, you notice that the code doesn't change at all here. What we're doing is a shutdown on success. We're forking off two requests. And what Structured Concurrency is going to do is if one of those requests throws an error, it's not going to propagate up the error and make the whole scenario throw an exception. It's just going to wait for the other thread to complete and see if it completes on success. And then it will wait and then clean up. If there's an error, it cleans that up and only returns the successful result.
Yeah, and so in this case, the server is actually letting both connections open. Then one of those connections that's open, the server is going to just shut down and close. And so this is like unexpected closure on a channel. And so that does result in an exception, but the race still does complete because it's essentially that shutdown on success just says, hey, an error happened. I'm going to ignore it and let all the other racers see who can actually win. So if a child throws an error, we just say, that's a loser. We're going to continue the race.
Yeah, and I'd say error handling in any kind of concurrency frameworks is always one of the most difficult parts that you don't think about. Like Go, you start writing Go and like Go routines, and you've got your channels, and you're like, this is really nice. And then all of a sudden you're like, well, how do I handle an error? What if I want to propagate an error up? And there's not like a clean way of doing that. And so this notion of just having a scope that handles that exception for you is so clean.
Okay, so then scenario 3 in Easy Racer is one where we say, all right, you really need to be non-blocking. You need to be able to open a lot of concurrent connections, and we're going to prove that with a scenario. And so in scenario 3, we do 10,000 concurrent connections. So you have to open 10,000 concurrent connections to the server, and then you have to race all 10,000 of those and get to the one winner, the first one that responds back. And so the Java Loom implementation of this one, very similar to what you've seen before. The only real difference is the way that we do put our children into the scope is we're going to 10,000 times do a scope.fork with that request in it. And so really this is the same race that you've seen before with scenarios 1 and 2, just the difference being 10,000 times we're going to make that request. And this does actually open 10,000 concurrent connections to the server and waits for the first one to complete and then cancels all of the rest. And so yeah, that all works pretty straightforward thanks to Loom and non-blocking I/O. This all just works as expected. Anything to add on that?
That's great. All right, scenario 4, we're going to do 2 concurrent requests again, but this time we want one of them to have a 1-second timeout. So we want to fire off these 2 requests, but one of those requests we only want to wait 1 second. We're like, if the server's going to take more than a second to process this request, let's just time it out and cancel it, because we don't want to spend too much time waiting for those. So let's look at
let me clarify one thing on here. So the scenario server will actually verify that you have opened 2 concurrent connections, and then after 1 second, one of those connections needs to get closed. And so you're not going to like pass the obstacle course unless you actually have implemented that correctly, where after 1 second you close that connection.
So let's look at the code for this. So this is scenario 4. This code's a little bit messy. It's a little hard to understand because you've got this outer scope, this inner scope. How do you think we could figure out how this works?
LLMs might be a good way to explain this stuff. So yeah, you can just right-click on there and say explain.
Yeah, so I've highlighted the code. I go into Amazon Q. I have the Amazon Q plugin in IntelliJ. I can just hit explain this selected code, and we'll see what it comes up with.
Turns out they understand this kind of complex, nested logic pretty well.
So it goes through, it's walking through the overview of what it's doing. But what's really nice is at the very end, it explains it, breaks it down. It says, in simpler terms, the code is like running 2 races simultaneously. Race 1, a runner, the inner task has a 1 second to complete the race. If they finish in time, the result is used. Not the other runner, the outer task without a time limit is returned. So that's what we see here. So that's really nice that Amazon Q has been able to kind of explain this code for us. So what we see is, what it's saying is this inner fork, we're just going to wait 1 second for it to complete, and that's that instant now plus the seconds and just 1.
So that join until is one way to do a timeout. There's another way to do a timeout, and I don't know how this is actually implemented under the covers, but some frameworks that do structured concurrency, if you have a timeout operation, the way that they implement a timeout is it's just a race. So a timeout is taking a task that you want to run, racing it against time, and if time completes before the task, then you've hit your timeout. And so you can assemble a timeout just with a race. But in this case, we could just do the join until instead of doing a race against time. If we did want to do a race against time, what we would do is do an inner fork and put a thread.sleep in there, because we can thread.sleep on virtual threads without any real significant overhead. And that would also assemble a timeout for us.
Yeah, the nice thing with virtual threads is you're not actually blocking an OS level thread when you do a sleep on it. It's actually just doing a time. And so it's not eating up resources and blocking on that thread. So it's really nice. Cool.
Yeah, so we've got the outer scope, the inner scope here, and we're going to race. So this is then going beyond just one level of a tree, but to multiple levels of a tree. And obviously in a real-world program, you may have structured concurrency that's many levels of a tree, and that's okay. It's all just going to work together, and as you have children that have other children, that all is you're going to get the expected results with those hierarchical structures.
Cool.
Anything else on that?
No.
Okay.
Scenario 8.
So with scenario 8 in Easy Racer, this one is getting into some more complex stuff around resource management. So one of the challenges often with concurrency is what you do with resources. You need to open and obtain a resource, you need to use a resource, then you need to make sure that you close that resource. And when you do this in a concurrent context, things can get pretty challenging and messy. And so with scenario 8, we're trying to show okay, let's do a race, but let's do it with a managed resource and see what that looks like. So, and the server may throw an error at any point. And so we also have to think about error handling. What happens if when I try to use the resource, I get an error? And so the servers, in this case, in this scenario, is going to actually try to throw some curveballs in with some errors there and make sure that you still clean up your resources, that all that stuff works as expected. So this is the Scala aux one. I want to show this one first because it provides a pretty straightforward way to do this. And so I've got some different methods here. First, I've got a way to make my request and get the response. But then I've got an open, and my open is just going to make a request to essentially /8 open. The result of this is going to be an ID, which is essentially my resource handle. And then I need to use that ID. And so this next one, use, that takes the ID there, that's going to make a request, use that ID, and then close is going to close that resource ID. So in the case of Scala aux, it's built on top of Loom. It's built on top of something we'll talk about in a little bit with scope values. But what we can do is establish a supervised scope. And the supervised scope allows us to say, all right, use in scope, here's my open, here's my close. My open is going to give me my ID. And then I can call use with that ID. And so now I've got this scope, the supervised scope, that's going to make sure that the open obtains the resource, gets it out. I can then use that resource, and then no matter what, the closure will happen because I'm in that supervised scope. So kind of this nice high-level DSL that provides this ability to do resource management with structured concurrency. So then, just like we've seen before, we're going to do a race with 2 different requests, and all of this works. I get the right answer. Things open and close just as expected. And so really nice way to visualize this resource management with structured concurrency. There's even errors that happen in this case, and all that just works. So that's our Scala aux one. Hopefully that helps lay out what the scenario actually does. The Loom one, the Java Loom one, gets a little bit trickier because I wanted to use an auto closable, and so basically the structure of this is very similar with a open, a use, and a close. But then I don't really love some of this. Like I'm obtaining my ID because I wanted to keep things immutable because I'm a functional programming nerd. Maybe not the right way to do some of this, but I get my ID and then I can make a request. Here's my error handling where I'm saying hey, if the response that I get back from using this resource is not a 200, then I'm going to throw an exception. And this definitely happens in this scenario where we do get an exception, or we do get a non-200 status code, and we need to make sure that that becomes a loser in the race. But then we also need to make sure that we close the resource that we had opened. And so then we've got our close method there for our auto-closable, where we make our request to do our close on that resource. So that's our rec class there that we have that's an auto-closable. And now you can do something very similar to what you've seen before. We've got our scope, our structured task scope with the shutdown on success. And then we're going to do 2 forks. I am going to do a try with resources because that's going to make sure that everything gets, the resources get managed and cleaned up. But now I'm just going to do that twice and do my fork and my join. And this all works as expected there. So that's the Loom one. And definitely like what's nice about this is I didn't have to do like finalizers. I didn't have to do a lot of manual management of the state and the closure and making sure that things get closed. I'm just using try with resources on an auto closable, and the cancellation, the error management, all that stuff happens for free and happens the right way. So
I think the resource management's a huge part of structured concurrency, of having a scope, a fixed scope where you're managing your resources and you know when they get open and when they get closed. And being able to share that resource is not only like inside that, the parent scope, but also the child scope is really nice.
And the cancellation being hooked into that so that when I cancel something, it does need to ensure that the resources get cleaned up. Yep. And that does happen with the try with resources in this case.
Yeah, and I know we're really ripping on Go here, but this is, with Go routines, you have a huge problem with this, because if I have multiple Go routines and then I want to share a resource, in one Go routine, I open a resource and then I want to use that in another Go routine, well, then I have to pass the resource between the different Go routines in a channel, and now I've created this implicit dependency between these 2 Go routines, but they're not really dependent on each other. So if one Go routine is supposed to open and close it, the other one's supposed to use it, and now I've got this weird interdependency, and then the parent Go routine, it cancels it times out for any reason, but the child doesn't know that it's timed out, and so now it's got this open resource that it doesn't close, and then I've got dangling resources. Yeah. So I don't have this nice way of encapsulating these resources. So.
Yeah, and I think that highlights a really good example of how, when you've structured things in this way, you have done a lot to prevent memory leaks and deadlocks and some of that stuff that are so common in concurrent programming. So a lot of benefits to using structured concurrency so that you avoid a lot of the pitfalls of concurrency. Yeah. Kind of puts you in the guardrails of the happy path.
Yeah, or you go back to the old days of Scala futures and try to do this with the Scala future. You have async callbacks, and which async callback, you have this callback hell and this whole hierarchy of callbacks. Which one of those callbacks was supposed to close the resource and clean up after itself? And so trying to figure that out. So
that's a good point. We haven't talked a whole lot about callbacks and that being kind of an older model of concurrency. And I think and probably many people here know, it just becomes unmanageable. And in structured concurrency, we have a much more direct and structured way of dealing with this that aren't callbacks.
Yeah.
So.
Cool.
Okay, moving on to scope value.
Right, so scope values are JEP, I don't remember what the number is. they're in Java 21. Scope values were basically a better implementation of thread locals. So the general idea of thread locals is I want values that are specific to each thread, and that thread can pull the values out and use that value anywhere inside of the thread without me having to pass that value all over the thread. This is particularly nice, for example, if I want to put in a request ID into a scope and then have that request ID used by a lot of the child scope. This is a little bit hard to read.
I think you can zoom. Can you
zoom? I zoom?
Maybe with pinch. No. Oh, that won't let me pinch.
Anyways, what we're doing is we do the thread execution. We create a scope value. And then before the initial, we define an initial container. So when we create a scope value, what it's doing is it's basically going to create this container that I can put my values in that all my threads are going to be able to use. And so each thread will be able to look inside of that container and say, where is my value and what is it currently set at? And so then when we create a new thread, we're going to create a new binding or a new scope value and put that inside of my container. And then when I execute the code within that scope, any code or any threads that are executed within that scope can look inside and find that value. And I can use that value with a get, so I can basically pull the value out, look at it continuously, and then continue the execution of that scope. And then if I'm exiting the scope, it's going to automatically clean it up. And if not, I'll be able to continue to use that with a get. So the advantages of scope values over thread locals are, first, they're immutable. Values cannot be changed once set. This goes back to functional programming concepts that are like referential integrity of like, I want to know what this value is. I want to set it once. And especially when I have like a lot of concurrent like tasks happening, and I'm trying to figure out like, where is it being changed and how's it being mutated and where is it being set? It's really nice if I can guarantee that I set it once, I know exactly where it's going to happen. And that way it makes it easier to reason about that code. Right, and I also want to automatically clean up when the scope ends. So if it's an object, something that I need to be released so it can be garbage collected, I want that to automatically happen so I don't have to think about that. And then thread confined, right, only accessible within the thread where they're set, or sorry, the threads where they're set. So it's only accessible inside of that scope.
So what's a common use case for scoped values? Where
I would say request IDs are the big one.
Tracing, yeah.
Tracing IDs are huge. Yeah.
So this is where you've, let's say you've got a request coming into your server. Yeah. That's going to get assigned a ID, but then that request is going to make other requests out to other services or call databases or whatever. Yeah. And you want to be able to pull a thread of execution. But these things are potentially asynchronous, potentially spawning off child tasks. And so you want to be able to maintain that scoped value aside from threads, but you don't want to have to pass it around through all the different calls. Maybe you're calling a library that you can't pass a thread ID into or a scope value into, a request ID into. And so this allows us to just like pass around some context through this like execution chain or a scope. Right? Is that the most common use case for this?
That's definitely. I think another use case is you're talking about web requests. When a web request comes in, oftentimes I want to like pull apart a JOT claim, look at who the user ID is.
The JOT is the security credentials.
Security token, sorry.
Yeah.
Thank you for clarifying. Yeah, the security token is that request comes in, I'll have a security token. I pull out, look at the security token, I look at the claims, I want to see who that user is, take that user ID, and I can store that in like a thread local context or a scope value context. And then anywhere I'm processing that web request, I can look inside of that context and say, who is this user? And I don't have to push past that context all over. So, I want to, update the database with that user's information. I want to update an order. I have that user information right there in the context without having to pass it all over. So
nice. So just like a way to like side door in some state across a scope of execution.
Yep. And especially like if I have like a user context, I want to be sure that that doesn't leak out to other requests. I want to be sure it gets cleaned up, right? Because I'm creating an object with all the user information. I don't want that to be left in and not garbage collected. So my run out of memory, that kind of thing.
So in scope values, we'll make sure that cleanup does happen correctly.
Yeah. So scenario 7, what we did is we added scope values to kind of just show what scope values do. What we're going to do is we're going to start a request, and then we're going to wait 3 seconds and then start a second request. So what we're basically doing is we fire off a request. We say, well, you know what? If we don't see the response back within 3 seconds, we really need that response, and so let's fire off another one and see if we can get that one back any faster.
So this is called hedging. This is a pattern that some people use to lower their P99 latency. So you can imagine that every once in a while, a request just gets stuck. The user does something, the request gets sent, and it's hit a server that has just gotten into a stuck state. Maybe the user gets unlucky and like hits a really bad GC pause. And so what you've got your P99 latency, and what you can do is say, all right, most of the time, these requests are going to come back, under this latency number, but some of the time they're not. And if I want to deal with that some of the time that they're not, what I can do is I can wait some amount of time, and if I have gotten potentially in a stuck situation, I'm going to fire off that second request to hedge that maybe that first one is just going to take a long time. But then you have a race of these two requests. So if things are under normal latency, then great, I don't even have to do anything. There's no second request ever sent, no resources used for the hedge. But if I am in the higher than normal latency case, fire off that second request, and now I race the two, and now I don't care which one comes back first. Maybe that first request does end up coming back first, or maybe the hedge request comes back first. Doesn't matter. Cancellation is going to happen either way. So that's the concept of a hedge, a common pattern for just dealing with that, the 1% of the P99 latency and being able to reduce that even more.
Yeah, and so, yeah. And to be able to understand what's happening, right, of like which requests are doing which, and like when they start and when they stop, because it's a little bit hard to understand. What we're going to do is we're going to use scoped values. Here we've defined a scope value. We're saying scope value new instance. So that's not creating an instance of a thread instance. That's creating a new instance of that scope value container that the threads will use to put things inside of. And then I've defined a common utility method called sendRequest. That common utility method does an operation ID get. So it's going to get out that scope value for that particular thread out of the container and be able to look up in this case, like the operation ID or the request ID. And then in scenario 7, when we run this, we're doing scope value where operation ID, and we're setting that to scenario 7, and then we're calling this run scenario 7.
So that's saying like, okay, when we're going to run the scenario 7, give us this particular operation ID. Like that's like the setting of the value into the scope or something, right?
Yep.
Okay.
Well, we could actually ask Q what it does too.
You could, but I think it's pretty straightforward. It makes sense.
Yeah. So then in scenario 7, it's really doesn't change anything inside of scenario 7. We're just doing, the standard, scenario 7, but because it's been wrapped with this scope value, it's going to now have that scope value available whenever I call like outer utility methods. And then we're doing 2 forks, right? The first fork just fires off the request, and then the second one, we're going to wait 3 seconds before firing it off. So what we're doing is we're saying...
So that's our hedged request.
Yep.
Is that one that does the sleep, which we're on virtual thread, so that's all fine. So if the first one completes in under 3 seconds, nothing ever happens there. We've just been in a thread sleep. It gets canceled. Like nothing wasted there.
The join will automatically shut down that second request. Yeah.
But if we're over 3 seconds, then we're going to fire off the second one and then race the 2. So that's our hedge.
Yeah. Cool.
So you want to run that one so you can see
Sure.
the scope values?
Yeah.
See how those end up getting propagated through. So this one's just running scenario 7 in this case and running against that Docker server. But yeah, walk us through the output there.
Yeah, and so what we're seeing is it's running scenario 7, sending off the request, and then inside that request, it's saying sending request for operation scenario 7. And so we're able to see which scenario is being run, and it's picked up that value out of the scope value container and showing us which scenario is being run so we can easily trace through and see. So in this case, it's pretty simple. Like obviously it's scenario 7, but if you imagine you had a more complex, like I had like multiple scenarios running in parallel, and I want to see which output is correlated to scenario 7 versus scenario 6, this would be really nice because I haven't had to pass that operation ID through. It's automatically picked it up out of the threads.
And at one point, you maybe had one of these that did the request ID kind of chaining
That's
as
in
well.
Scala.
So we could have. Oh, okay. Oh, that's the next one. Am I getting ahead?
No.
No, we're not showing that one.
We could actually. We have an extra minute, so.
Sure. Let's check it out.
If you want to talk about it, I can pull the code up really quickly.
Yeah.
Do we have this? Is this the right version?
Maybe. Oh, it may not be.
No, it is.
Oh, it is. Great. Okay.
Yeah.
So
do you want?
yeah, so this is built on top of scope values. They call it a fork local, and a fork local allows us to put a value into this request ID. And then very similar to what Ryan showed before, we have this scenario request where we're going to get our request ID out. We're going to make our request, and then we can output on the map response there that value. So then in scenario 7, we do a supervised scope. So this is setting up the scope there. So very similar to what we did with the resource-based one. And then we can say, all right, request ID supervised where, give it the ID. And now we're in that supervised scope where we have that ID accessible, so we can propagate that ID through. Did I get that all right?
Yeah.
Okay.
Exactly.
And then the delayed request is the same thing with the sleep. So
Yeah. Yeah, we're just setting different request IDs on each scenario. Let's update this. We run scenario 7.
You want to run it. Let's make sure it works. Yeah, so then we'll actually see the different IDs there. Okay. I guess we kind of showed it with the first one with the different request IDs, but there we go. There's the hedging one, so we can see what happened. We made a request. We got our request ID set into the scope. You'll see that it's different IDs right across those different ones. So it's working just like you'd expect, and that's, I think, the nice thing about structured concurrency is it generally just works like you'd expect, unlike normal unstructured concurrency.
Yeah, so you see here, like we're setting the request for 3E47, setting the request for 95DA, right? We only see the response for 3E. We never see the response for the other thread because the other request because it's been shut down.
Got canceled.
Yep.
Yeah. But it propagated that state through. So
yeah.
Yep. So a different way to handle that. Okay, I want to show one other one since we're in here, which is scenario 9 in the Java one. So we've been talking about the race one where we want to go from many tasks down to a winner, a single one. But what about in the case where we want structured concurrency where we go many to many? And so this one, what we do is we create our structured task scope here, and we don't do in the previous ones you saw structured task scope dot shutdown on success, and in this one we don't specify a shutdown on success or a shutdown on error. We just leave it as a structured task scope, and then we're going to make 10 requests. So I'm doing 10 forks to make 10 requests out to the server. And so in this scenario, what we have to do is make 10 requests concurrently. Each of those returns like a letter, or 5 of the 10 of those return a letter. And so we need to do not the many to one like a race, but a many to many where we want to preserve all those. So we're putting all those into the scope with the scope.fork, and then we're doing our join, so essentially block, but don't really block because we're on Loom, until all those have completed. And then I'm going to use streams to get all of the responses out. I do need to do some filtering because not all of them were successful, but you can see filtering, and then I need to sort them to get to the right answer. So that's how we would do the many-to-many cases, the structured, just the regular structured task scope, not the shutdown on success. So shutdown on success if you want to do a race, or shutdown on error.
So it's kind of like many to one and then many to many. So I have like races many to and many inputs to one output, and then the structured is many inputs and many outputs, so a whole list of outputs. Is that the way you think about it?
That's right. Yep.
Okay.
That's it. Yeah. Okay, so that's what we had. The code is all up on my GitHub. So that's GitHub. Oh, actually, this version of the code is on Ryan's GitHub, but we'll go to that. Retro Ryan Easy Racer, and the slides and stuff are up there if you want to go check it out. So you can see all the different implementations of those. So yeah, feel free to check that out. We do have 2 minutes for some questions. So any questions about structured concurrency? Yeah.
Really nice talk, thank you. Because there are only 2 built-in policies for structured transport, did you try to implement your own policy? Because Alan and Ryan said it's pretty sophisticated to do it. Just curious if you tried to do so.
I've not tried to implement my own policy on the Loom structured task scope. maybe be possible. I think generally there are two policies, which is the what do you want to do in the case of an error? Do you want it to be considered a loser, or do you want to propagate that error? And then with the other approach, which I showed at the end there, just the regular structured task scope, you could certainly implement any policy, whatever you want to do. You're going to make all the requests, and then it's up to you to decide how you then want to transform all the things that you get back down to something else. But yeah, I think race is kind of the typical one that does race on success or race on close on shutdown on error, and then the other many-to-many one allows you to do whatever you want. So
I'd say PRs are welcome, and we'd love to see an example of using that. So
we could add more obstacles to the obstacle
yes,
course. That's certainly
yes.
possible.
It could be really interesting, actually.
Okay, thank you for the question. We'll wrap up. I'll be at the AWS booth if you have more questions following that, but hopefully that was useful. Thank you.